Alright, so let's get into it here. I've written some notes. In fact, it took me most of Friday to do these. And these notes just basically go over what I've said about vectors. And so many of these things I've already said in class, so I'll try to go quickly through this. And also, if you can't quite see things here, my apologies, but remember a PDF of this has been posted in Blackboard. And it's much easier to see, of course, if it actually had printed out correctly, but unfortunately some of the, I don't know what, it's not, the toner or whatever you want to call it in my printer is not, it's not quite right. So I think we need to buy new something or other. I had to take the cyan out and do something to it, and so it gets a little bit better midway through this. But anyway, let's get started. So first of all, I talk about Euclidean space. Euclidean space is just a name for our usual plane or 3 dimensions. You can identify those, like I say here, with ordered pairs or ordered triples. And of course you can extend that. You can talk about ordered n-tuples as they're called. And I'll try not to say too much about Rn in this talk because our focus is primarily on 2 and 3 dimensional space. But anyway, the key feature here of a an ordered pair is that if you have equality, right, then that demands that it's not enough to have 1 equals 1. Like, that's great. 1 equals 1, great. But the fact that 2 is not equal to 3 is enough to disqualify the equality of these 2 triples. Right. So these 2 points in 3-dimensional space are distinct because they have a distinct z component. Right. And likewise, if you knew that 1, 2, 3, 4 was equal to a, b, c, d, then that would tell you 4 things. It would tell you a is 1, b is 2, c is 3, and d is 4. All right. So conceptually, a point is something without finite extent. It has no width, height, or length. And of course, we can characterize each point in terms of its components. So yeah, I'm sorry. It's just the printer's just completely let me down here. But of course, we can talk about x and y and z components. You guys get that. Here's a picture of it. So if you've taken notes already in the previous about 5 lectures or so I've given, there's probably not too much really to add here. So you can just kind of read through these notes, make sure you're not missing anything. Here, if we have the point ABC, that means it's like a over in the x, b over in the y, and c over in the z if a, b, and c are positive. Of course, if any one of these is negative, then it puts it on the other side of things. But and the term, why we call it Euclidean space? Well, that emphasizes our notion of distance. All right, so technically speaking, you could take these same points, set of points, and you could give it a different notion of distance. Then it wouldn't be Euclidean space; it would be something else. But in Euclidean space, we use the usual distance formula, like the distance between. So you take the sum of the squares of the differences between the points, like we've talked about, hopefully in middle school or something like that. In 1 dimension, the absolute value of the difference of 2 numbers is the square root of the difference squared, actually, so it's even the same for 1 dimension. So we take the sum of the squares of the differences between the points to get the distance. That continues to be true in 3 dimensions, and even n dimensions. And here's a little picture that I went through in class, right? Not exactly the same notation, but same idea. To get the distance from the origin to the point, you can think about it in terms of 2 triangles, the triangle in the xy plane and the vertical triangle, like that, which has z as that distance, but it's got the square root of x squared plus y squared as that one. And of course the hypotenuse is the length from the point 1 to point 2. And that's how we get the formula square root of x squared plus y squared plus z squared for the distance from the origin out to x, y, z. So that's pretty much all I got to say about points. All right, so points are just labeling. It's fun. I almost can't say much more about it. It's essentially fundamental, you know. Now vectors, on the other hand, vectors connect points, right? A vector you could think of first of as a directed line segment. So the vector from P to Q is given by Q minus P. We take the difference of the components, right? We can define addition by adding the components. We can define scalar multiplication by multiplying the components. the length is the square root of the sums of the squares of the components of the vector, right? And we define the unit vector by taking the vector and rescaling it by 1 over its length, by multiplying it by 1 over the length. Notice that we use the symbol here. So we use the symbol here without the vector to indicate the length. That's a number, the magnitude of the length of the vector. Another notation for that is just double bars for length, all right? And anyway, v hat, it's not come out very good here, but v with a hat over it. Here, I'll write it again. So, vector v is equal to the magnitude times its unit vector, v hat. Here, v hat is 1 over the length of v times the vector v. All right, now, I think I've added some examples down here. So if we have point P minus 2, 4, point Q 8, 7, then PQ we do 8 minus a minus 2 and 7 minus 4 to get the components of the vector, which is the directed line segment from P to Q, and it has components 10 and 3. The magnitude of that vector is square root of 109, and that's also, of course, the distance from P to Q. Another example, if I have vector A is 1, 3, vector B is minus 1, 0, then A plus B, I just add 1 to minus 1, 3 to 0, and I get 0, 3. And you can calculate the magnitude of A, square root of 1 squared plus 3 squared, square root of 10. The magnitude of B is just 1. So actually B is already length 1, so it's already a unit vector. And so the unit vectors, we do 1 over a times a vector, which is 1 over square root of 10 times 1, 3, which of course you could write out in components as 1 over root 10, 3 over root 10, and, well, b hat is very silly. It's just 1 over 1 times b, so b hat is equal to b. B and its unit vector are the same. Okay? Now, another example. If a is the vector 3, 4, then the length of a is the square root of 3 squared plus 4 squared, which is square root of 25, which is 5. Consequently, the unit vector in the a direction is 1 over the square root of 5. This will be 1 over 5 times 3, 4. All right. Here's one that's a little bit more interesting. Find a vector b with length 7 in the same direction as 1, 1. So the way I do this is I go, okay, well, a hat is 1 over root 2, 1, 1, because the length of a is square root of 2. And so if I want a vector of length 7, I just take 7 unit vectors and string them out together. In other words, I put 7 times a hat, and that gives me a vector of length 7 that's in the direction of a. So that's a, I mean, I can, let me just draw it out, actually. So the point is, like, a hat is length 1, right? So if I want a vector of length 7, I just keep going that way, 7 of them. I'm trying. 1, 2, 3, 4, 5, 6, 7, right? So b equals 7 a hat. That gives me a vector of length 7 in the direction of a. Okay? So, like, this is how vector length works. If you calculate the length of vector b, that's the length of 7 times a hat. So you can pull the 7 out, and the length of a hat is just 1, so that's 7 times 1, which is 7. Now, I talk about that later in these notes, but I'm just throwing that in here. Anyway, it should be like geometrically obvious that if you take a vector of length 1, multiply it by 7, you get a vector of length 7, right? Because it's like adding the vector to itself 7 times. All right. Now, you could also do an algebraic approach to that problem. You could say b is equal to ka and like solve to make the length of b be 7. But anyway. So I should point out, as I have pointed out in class, excuse me, that there's a natural correspondence between like the point w1 comma w2 and the vector w1 comma w2. So I know you probably can't see it. I can barely see it myself here. So the point W1, W2, and the vector W, W1, comma W2. So like, it may not seem like I'm saying anything, but the point is, you know, it has no extent, right? It's the point right there. The vector is the directed line segment from the origin out to there. So the vector has an extent. It's got a length, if you will. We also call the length of the vector the magnitude, right? So that's one thing we should keep in mind, is we can identify a point with a vector from the origin if we want. That's often done in physics and engineering. And I would also warn you that other texts use bold to denote vectors, but I try to use either the over arrow, or for a unit vector I use the hat. How do we add vectors? Tip to tail, right? So we take, this is vector v. So here's vector v like this. That's v. And then if you add to that vector w, which is up here, so I'm putting the tail of w at the tip of v, all right? Then the green one, oh man, I got no green markers on hand. Where are my markers gone to? Children stolen my markers. I believe. Well, we'll have to make do with pink. It's not great, but it'll have to work. So this one, ooh, actually this one's kind of dry. So that is v plus w. Right, so we go v, then go w, that's v plus w. That's how to add them geometrically. And that also lines up well with the addition rule that I already wrote on the previous page, right? We have scalar multiplication. If you want to think about it geometrically, here's the vector v in red, and then if you have c1 see, I see greater than 0, but actually from my picture, c1 would be greater than 1. Technically speaking, this picture has c1 greater than 1, and for this picture, c2 looks like c2 is about equal to -1 in my picture. All right, but so if the constant is negative, it puts it in the opposite direction. If the constant's positive, it puts it in the same direction, but it rescales the length. All right, generally speaking. Of course, if you multiply by 1, it doesn't rescale the length; it just leaves it. Let's see here. Here's an example. So if I add vector a plus vector b plus vector c plus vector d, that gives me a plus b plus c plus d is this r vector, which physicists will call the result. I used r for resultant. All right. We talked about in class how if you took the vectors that went around a closed shape, that they would add to 0. Right. That was one of the examples. Next down here, I have a picture. It's now they've all kind of come out. There's something funny about my red, I guess. The ink, I think it's supposed to be red, but somehow it's become kind of rainbowy since the printer's not quite working. So that's B, and so we take A plus B minus A, right? What do you get? You get B again. Right, so that the fact that this equality holds goes to show you that this green vector has to be the B minus A vector, right? Anyway, that's sometimes an important thing to know. If you want to get from a vector A to a vector B, like the endpoints, you can use the vector B minus A to connect the end of A to the end of B. All right. Another thing that's important to mention, and the printer has again let me down, is that if you have a vector, we allow ourselves oftentimes the freedom to move that vector around as long as we maintain its direction and its length. All right, and so we can also do that in 3 dimensions, although it's harder for me to illustrate. But basically, you know, I can. Well, here, coming right out of the page, right? So coming right out of the page. Think of that as a vector, right? I can move it straight up towards the camera like that. It's still the same vector. Whee! Or I can move it here, here, here. So same pointing up 1 unit vector. This is called parallel transport for what it's worth, but of course if we wish to keep track of the base point of the vectors, then you need an additional comment or notation. All right. One example of a force of a physical problem that involves vectors at different points is, I think about like if I was trying to rotate this, and I push on it like here, like that. Well, then I think of the radius arm for the motion as being based on where my fingers are pinching the marker, right? But I think of the force of application on the lever arm as being right here. So, that physical problem is one where you think about a force applied here, but the radial arm on which that force is being applied is based here. So we do find problems in physics which have vectors based at different points. It's not hard to find such problems. So it's something we got to deal with. 3-dimensional vectors, so this definition here just reiterates everything I said about 2-dimensional vectors, but for the 3-dimensional case, basically I say to find the vector from P to Q, you take the vector of the difference between their components, 1, 2, and 3. You can add them by adding components. You can scalar multiply them by scalar multiplying components. And the length of a 3-dimensional vector, you need the sum of the squares of all 3 components. And we construct unit vectors in just the same way we did before by dividing by the magnitude. So, for example, if this is vector A is 1, 1, 2, minus 2, so that has the length of A, which we just use A for, square root of 1 squared plus 2 squared plus minus 2 squared, which is 1 plus 4 plus 4, which is 9. Square root of 9 is 3, so the length of A is 3. And the unit vector of A then, we just divide by 3. 1 over 3, 2 over 3, minus 2 over 3. This right here is a vector of length 1 in the direction of A. If you wanted to construct a vector B, length 18 in the direction of A, just do 18 times A hat, which would give you 6, 12, minus 12. All right, and it's kind of neat. Apparently, 6 squared plus 12 squared plus 12 squared is equal to 18 squared. So you can check on that if you want. All right, so there's that. Now, next up, decomposing vectors into components. Now, I've talked about this, but I think I may be, in this bit of the notes, sort of taking a new, what's the word? New perspective on it, perhaps. So if we have any vector in R2, we can break it up into a sum of the x hat vector and the y hat vector, which is the 1, 0, and 0, 1. Of course, I think in class I have more been using the standard, I hat equals x hat. All right. So in these notes I use x hat because, well, they're my notes. So I'm using my notation. Anyway, y hat 0, 1. So this is I and j. This is in 2 dimensions. For 3 vectors, they get an extra 0, and then there's also the k hat, which is 0, 0, 1, which I would call z hat. But anyway, you can build the vector from a sum of a x hat and b y hat here. So that's the decomposition of the vector into a sum of its x and b vector components, as I define here. And so vector components are themselves vectors. And you can literally think of the vector as being built from the tip to tail sum of its vector components. Here's another picture of the same calculation. So I can build from a x hat plus a sub y hat. So here, this vector, if I was to write it out, is simply a sub x, a sub y. That's another notation you oftentimes see in physics, like for x and y components. They use I tend to use 1 and 2 in math, but you could put an x and y there. All right. So, excuse me, drink some of my tea. So, example. These examples are really pretty unexciting. So here is 2 minus 3. So that means 2x hat is the x component of it, and 2 is the scalar component of v in the x direction. Likewise, minus 3y hat is the y vector component of v. All right. And of course we could draw it if we wanted to, right? So this vector would look something like what? Oops, bad choice. Over 2, down 3. So it's something like this, right? Okay, so that's the, so I'm doing my usual x and y, xy plane there. All right, so there's that problem. Find a vector A of length 10, which has 6x hat as its x component, x vector component. So I really, to be clear, I should say this is a two-dimensional problem, all right? So we're seeking y such that, so if 6x hat is its x vector component, so that puts a 6 in the first slot here, right? And so the question is, what's y? Well, I know that it has length 10, right? So a squared is 6 squared plus y squared, which is 10 squared. So that makes y squared equals to 10 squared minus 6 squared, which is 100 minus 36, which is 64. And so taking the square root of that equation gives me y is equal to plus or minus 8. So in fact, we find two vectors which solve this problem, namely 6 comma plus or minus 8. There's a problem in your take-home quiz which is very much like this. I say find all such a, I think. Maybe it's problem 5 or 6, I can't remember which one, but there's a problem just like this in the take-home quiz. All right. Now in 3 dimensions we have x hat, y hat, and z hat, and so we can build a 3-dimensional vector from the sum of the x component vector, the x vector component, the y vector component, the z vector component, like that. You can visualize that in terms of the tip-to-tail addition here. So ax hat, a sub x x hat plus a sub y y hat plus a sub z z hat gives us the whole vector a. Again, just to be clear here, this vector a is equal to a sub x, a sub y, a sub z, and what we're pointing out is that you can write that as a sub x x hat plus a sub y y hat plus a sub z z hat, and you can also think of that directly as the tip-to-tail addition of that, of the blue, the red, and the green vectors. All right. And once more here, I define the scalar and vector components, and got a couple easy problems here, examples rather. 1, 2, 3, we can build from this, which is x hat plus 2y hat plus 3z hat. Great. Find a vector of length 5, which has 2y hat as its y component, and 3z hat minus 3z hat as its z vector component. So what's missing is the x, right? So we've got x, 2 minus 3 as length 5, so that means a squared is equal to x squared plus 2 squared plus minus 3 squared, which of course is 5 squared. So 25 minus 13 is 12. And so x squared is 12. Take the square root of that. It gets me plus or minus 12. Root 12, rather. So we find two solutions. Plus or minus root 12, 2 comma minus 3. Those are... I don't know if it's my... I'm not sure if it's the printer or if it's just my, my typo here, but there's supposed to be a comma there. Anyway, so yeah, it's because it's a 3 vector, which has 2 commas in it, you know. But anyway, plus or minus root 12, 2 comma minus 3, those are the vectors which have 2y hat as the y vector component, minus 3z hat as the z vector component, and have a length of 5. Okay. So finally, let's conclude this section by discussing how trigonometry plays into all this in terms of breaking the vector down into its components. This is a huge part of like introductory physics, certainly like first semester physics. One of the main skills I always want students to learn, and there when I teach it, is how to break vectors into their components. And it's just right triangle trigonometry, really. So if I have a vector that goes like this, and I have the standard angle theta there, then the magnitude is the hypotenuse length in this picture. So v cosine theta is the adjacent side, and v sine theta is the opposite side. But of course that's the x component, and that's the y component of the vector. And so, you know, I have some examples down here which are based on that idea. At length 5, angle pi over 3, so v cosine theta is, 5 halves, and v sine theta is 5 root 3 over 2, since we're working with 60 degrees. So in view of this diagram, we see that the vector actually is 5 halves, comma 5 root 3 over 2. Okay? Another example, this time the angle is over here, but it's really the same song and dance, because remember, when theta is between pi over 2 and pi, or 90 and 180, we have that the sine theta is positive and the cosine theta is negative, just like we want. We want a negative x component for the vector and a positive y component for the vector, and that's what we get from using v sine theta and v cosine theta. And specifically, we get, so I said length 2 and 5 pi over 6 for the angle, then so that makes you like 30 degrees above the negative x-axis for what it's worth. So we get cosine is minus root 3 over 2, which gives us, the 2's cancel here. We get minus root 3, and sine of 5 pi over 6 is actually 1/2. So that gives us 1/2 times 2, which is 1. So the vector in question is minus root 3, comma 1. And that makes sense because 5 pi over 6 is in quadrant 2, and that was consistent with the picture that I just put away, like that. So let's see here. In general, what's the story? So I give you a couple of examples, but generally speaking, if we have a vector which is non-zero, we can describe the vector in terms of magnitude and standard angle. If we place the vector at the origin, then from our discussion of polar coordinates, we know that v1 is v cosine theta and v2 is v sine theta. All right, and so the vector is actually v times cosine theta sine theta, right? Because we can factor the magnitude v out. But we also know that the vector is v times v hat. So if you look at the fact that, if you just look at it, this is equal to that, right? And so since the v is non-zero, we can divide this equation, these are equal, by v, and that gives us that v hat is cosine theta sine theta, which is really totally unsurprising if you start thinking about it, because, of course, cosine theta comma sine theta was a point on the unit circle. So now we're saying that, if you look at the point on the unit circle, let me see if I can foolishly try to draw it here, right? This point on the unit circle, we can either describe it as the point on the unit circle, right? Remember, it was cosine theta sine theta, right? Or we can describe it as a vector of length 1, which points from the center of the unit circle out to the point corresponding to that vector. So anyway, I'm not saying anything terribly profound here. I'm just saying it's not at all surprising that cosine theta comma sine theta is a unit vector, okay? Because it points to a point on the unit circle. So here's an example. Suppose v has length 37, that's directed at standard angle 295 degrees. Then the unit vector in the direction of v is simply cosine 295, comma sine 295. That's it. All right, that brings us to the dot product. So the dot product is a nice one of our two interesting vector products. We have the dot product, we have the cross product, right? So the dot product produces a number which is produced by v1 w1 plus v2 w2, or in 3 dimensions you add v3 w3 to that. All right. So dot product takes in two vectors and it outputs a number. Here's a couple of examples. 3, 4 dot 7 minus 2 is 3 times 7 plus 4 times minus 2, which is 21 minus 8, which is 13. All right. 1, 2, 3 dot 1 minus 1, 5. We get 1 times 1, which is 1, 2 times minus 1, which is minus 2, 3 times 5, which is 15. So we get 1 minus 2 plus 15, which is 14. Okay. And, try not to talk too much about it, but it is true that you can define the dot product for Rn. And most everything I'm saying here generalizes naturally to n dimensions. But not true for the cross product, okay? That's only true for dot product. So properties of the dot product: it's commutative, it's distributive, cross addition both ways, you can pull numbers out of it, it's non-negative, like the dot product of a vector with itself is greater than or equal to 0. there's no null vectors, so like if a dot a is equal to 0, that's true only if and only if. That's a shorthand for if and only if. So anytime you see if and only if in a sentence, you could replace it by is essentially equal to this symbol. I can't draw the symbol. What's wrong with me? Let's try that again. This pen isn't quite right. Anyway. So I think we proved a little bit of that in class. Here's one of them. You know, why is the dot product commutative? Well, a dot b is a1 b1 plus a2 b2, but since these are just numbers, you can commute them, which is b1 a1 plus b2 a2, which is, can by definition is b dot a, so a dot b is equal to b dot a. Why is it non-negative? Well, a dot a is a1 a1 plus a2 a2 plus a3 a3 for a three-dimensional case, right? Which is a1 squared plus a2 squared plus a3 squared, and that is clearly greater than or equal to 0. So, I mean, that's pretty much it. Notice that we now have a newfangled formula for the length of the vector. We can take the square root of the dot product of the vector with itself. Another thing that I more often use for like a proof or something is that if I want to calculate the square of the length of a vector, I just take the vector dot product with itself. Like this right here I often use in proofs and or calculations. So the properties of the vector length, I circling back to that, talk more about properties of vector length, which is, vector length is also known as the norm. Like, you know, you've seen the word normative used in your other classes, I'm sure. So norm defines length. Anyway, so properties of the norm, if you pull a number out of vector length, you pull the absolute value of the number out. You have this triangle inequality, so-called Cauchy-Schwarz inequality. I mentioned this one in class. It's the length is non-negative, and only the zero vector has zero length. Those are properties of the norm. Now I've skipped. I didn't put the proofs of these in this notes for you. If you're interested in the proofs, you can talk to me about it. It's also in my Calculus 3 notes if you're impatient. You just want to look at them. But I think the proofs are a little bit kind of, you know, beside the point for this class. Really, I just want, the takeaway I want for you guys is, you know, what is a vector conceptually, how do we add them, and how do we use the dot product and cross product? You know, how do we break the vectors down into components? I think those are the main goals for us this semester, vector-wise. Notice that the dot product of the unit vectors with themselves work out really nice, like x dot x hat is 1, y dot y hat is 1, z dot z hat is 1. But on the other hand, x dot y hat or x dot z hat or y dot z hat, these are all 0. So if you know these basic ones, then you can calculate the dot product just using that in like algebra. I mean, this is like a stupid way to do dot products, obviously, because it is so much faster to just go, you know, 1 minus 2, 3, dotted with, let's see here, we're looking at 5, 0, 9, and you just go, okay, well that's 1 times 5 plus 0, because there's a 0 in the second one, right? Plus 3 times 9, which is 5 plus 27, which is 32, right? So that is obviously faster than like working it out like this. But I'm illustrating a principle here, which is you can use algebra of the dot product paired with your knowledge of the dot product of unit vectors to calculate dot products if you do so desire. Okay? This idea is more interesting for cross products. There are actually cross products which are faster to do using this sort of technology, if you will, than the standard formulas. But orthogonal vectors, what's an orthogonal vector? Orthogonal vector is another fancy word for perpendicular vectors. So two vectors are perpendicular if their dot product is 0. And a set of vectors which are pairwise perpendicular, pairwise orthogonal, and all have unit length is said to be an orthonormal set of vectors. Like the unit vectors. So what's an orthonormal? A good example of orthonormal set would be like this one: x hat, y hat, z hat. This is orthonormal. It's orthonormal set because the dot product of any two of these is 0, and the length of each one is 1. So I point out that if you take the dot product of a vector with the, I think I'm missing a 1 right there, maybe the printer. Anyway, dot product of a vector with the unit vectors, it picks off the corresponding components. Oh, I'm sorry, I missed this. This, my bad, guys. I've tried to edit these notes and remove all of the offending fancy hieroglyphic math, and I've failed here. So this is delta. This is the Kronecker delta. Delta ij is 1 if I is equal to j, and it's 0 if I is not equal to j. And it turns out that symbol really is the DNA, if you will, of the dot product, but I'll just leave it. You can ignore this bit right here. It's not something I expect you guys to know. Anyway, so here's how the vector breaks into its dot product. So like we can take dot products with x hat or dot product with y hat, and that gives us the x component or the y component, scalar components. And then finally I'm circling back yet again to the sine and cosine, right? So we can write a vector as cosine, okay, something's lost in translation here. I'm supposed to have a, this should be, I'm assuming, let's put here, if the length of V is equal to 1, then the following thing makes sense. So if the length of V is 1, then V is just cosine theta x hat plus sine theta y hat, right? And on the other hand, it's V is equal to V dot x hat and V dot y hat. So anyway, the point is cosine theta is V dot x hat and sine theta is V dot y hat. But I'm sorry, I'll have to fix this and repost the notes for you guys. I really meant to put a V here and a V here, and there should be a V here, and there should be a V here. Well, goodness. No, I guess I was. I'm sorry, guys. I'm having a crisis of indecision here. I do think I'm thinking unit vector because my point is anyway, you can ignore these sentences. They're not wrong, but they're not helpful. So sorry, guys. Anyway, so if we have a vector, this next sentence though is useful. If we have a vector which is a, which we, of course we can write as a cosine theta, a sine theta, factor the a out, right? So the point again here is that the unit vector of a is cosine theta, sine theta. This is something that would be good for you to know. And there are homework problems in the take-home quiz that are using that idea. So sorry about that. All right, so if here's an example. If V has length 10 and the angle is minus pi over 6, then V hat, all right, is cosine pi over 6 comma minus sine pi over 6. I use the fact that you can pull the minus out for the, since sine is odd, and that gives us root 3 over 2 comma minus 1/2. Notice that to calculate V hat here, what did I not do? Didn't need to know, I did not need to know that V was equal to 10, right? That the length of V is 10. That's completely irrelevant. Actually, once you tell me the direction, that suffices to fix the unit vector. So if okay. So my next example is that again. All right. So I guess I'm really grinding that axe there, aren't I? Okay. So we can define angle measure via dot products. Pointed this out in class, right? The inverse cosine of a dot b over ab is the angle, and this right here basically is the argument I shared with you guys in class about the law of cosines. I make a slight, what's the word, conceptual modification of that argument, which makes this argument apply to like a general higher dimensional context. But anyway, it's the same argument. Basically, the point is that the when we look at the law of cosines applied to, you know, this picture, A, B, and C, then that makes C equal to B minus A. And so when we take the dot product of the vector C with itself, we get, and we use the law of cosines, and we get a relation between vector lengths and the cosine of the angle. And we end up with this formula, which is simply that A dot B is also AB cosine theta. All right, so, and I showed you how we can use that to find the angle between vectors in class. All right, so some fun facts. If A and B are non-zero orthogonal vectors, the angle between them is pi over 2 or 90 degrees, right? Because that's when you get cosine is 0, when you put in 90 degrees. Parallel vectors, that means A dot B is equal to AB because cosine of 0 is just 1. All right, so angle between parallel vectors is 0. The angle between anti-parallel vectors, that means they look like this. Anti-parallel means like this. Okay, so if they're anti-parallel, that means that theta is 180 degrees, or pi if you like, radians. And so in that case, cosine of 180 is minus 1, so A dot B is equal to minus AB. All right. So we can check for perpendicular, parallel, anti-parallel by those cases. And I think I have asked you some questions in the take-home quiz about whether two vectors are, you know, parallel, perpendicular, or neither. So like here's one. If I've got vector minus 5, 3, 7, and B is 6, minus 8, 2, are these vectors parallel, anti-parallel, or orthogonal? A dot B, I mean the answer could be none of the above. A dot B is equal to minus 40, so we know that they're not orthogonal because the dot product is not 0. And they can't be parallel as the dot product sign indicates the point is more than 90 degrees opposed. Are they anti-parallel? Well, minus AB is equal to the square root of 8,932, which is not equal to 40. So no, they're not anti-parallel either. What's the angle between them? Notice if we just calculate the angle between them to start with, you can answer all the other questions, can't you? So the easy way to do your homework when I ask you to find the angle and answer the question, is it parallel, anti-parallel, or orthogonal? We'll find the angle first, and then you can answer the question parallel, anti-parallel, or orthogonal anyway, right? Because if angle is 0, they're parallel. If the angle is 180, they're anti-parallel. If the angle is 90, well, then they're perpendicular. But anyway, for these ones, A dot B over AB is minus 40 over square root of 8,932, inverse cosine of that fraction, and we get about 115.5 degrees. So there you go. Now we worked this example I worked in class, as you may recall. Find the angle between the back leg and the diagonal from the origin pointing out to the front corner of a cube. I did it for unit length in class. Here I've done it for length alpha, but the story is the same, 54.74 degrees. And then here I have I list a few examples from physics, like, you know, force dot displacement gives us work done by a constant force. There's another work example here. Great. And then just some then I just have some other examples where the dot product is used for a formula in physics, like kinetic energy is 1/2 mv squared, which is 1/2 mv dot v. The force, if you have a net force F developing velocity v on some particle, then the power that force applies to the particle is v dot f. If you take the current density dot the area times the normal to the area, well, that gives you the current that flows through that area. If you take the electric field and dot with the area vector, that gives you the electric flux. If you If you take the magnetic field and dot with the area vector, you get the magnetic flux. All of these are important to second semester physics. Okay, and that brings us to the cross product. All right. Okay, so I think I'm gonna start afresh here because this is this deserves a little bit more time. So, and up to now we've pretty much just reviewed things I've already said in previous classes.